Hello everyone, welcome to Dakshana e-classroom program. So in last lecture we started talking about inductance or inductor, and we discussed what is exactly inductor. So inductor we simply call basically a coil is termed as an inductor, is it? So in normal terms, like if we are having a coil where some wire is bounded like this, so this is called inductor in physics. Basically the rule of this inductor, this device, is that it has some property, and that is basically if a changing current is linked to it, or if a flux is linked to that, and if it want to change, then it has property to oppose that. It want to keep it constant, that is, and we measure that opposing property, we define that opposing property in terms of inductance, right? And we discussed, we calculated the self inductance, means when current is going in this coil itself and that is changing, that means flux in the coil or through the coil is changing because of current in itself. So that will be opposed by the coil itself, and we call that opposing property, or like we measure that opposing property in terms of self inductance. And we define for a solenoid the self inductance, we denote it by L, and that comes out to be mu naught into N square into A is the area of cross section times L, where N is the length, mu naught is the property of basically permeability that depends on the medium, and N is the number of turns per unit length. So we discussed up to here in the last class. Let's continue from here onward. We did not talk about much about it. Yes, we saw that like inductance, it's a geometrical property. It's not like it does not depends on the current, it depends on the medium, it depends on some geometrical parameter of coil. Okay, so I'm going to talk more about inductor. Okay, so normally in a mathematical term, we represent the notation of inductor is mathematically, we like this is how, this is the symbol of inductor basically, or you can write symbol. Just like for resistance, we know actually this is resistance, right? So exactly in same manner for inductor we write it this way. Actually it's like circular, is it? Curve. It's here like zigzag, and here it's different. And when some current is flowing through this, let's say I current, then we can write the flux through this, flux linked to the coil, or coil means inductor. Inductor in terms of physics we call coil as inductor. Then I can write phi is equal to L times I. Clear? So similarly, if let's suppose constant current is linked, then definitely there will be flux through the coil, is it? So if I is constant, then that means phi is equal to Li is also constant. Means even when I is 0, then also L will be there, because L is not depending on I, it's property of, it's like a geometrical parameter. So if coil is there, automatically it has inductance, is it? And its self inductance is L. So now if current is changing, right, then what will happen? Through this flux will change and it will try to oppose. And how it will oppose? It will try to oppose by inducing EMF by Faraday's law. So whenever changing magnetic flux is linked, there will be induced EMF. So exactly that, like why and like who will induce, and that we can say it's a property of the coil, is it? We have like seen it earlier also, like why changing magnetic flux result in EMF. So both two cases we have like seen two ways. One is when the conductor is moving, actually in that situation we can understand that by the force on a charged particle, force on electron. Another case when conductor is at rest and magnetic field fields is changing, in that situation it's because of the induced electric field. So I hope you are understanding why that is also happening. We are now in position to understand that. Now next point is that if changing current is linked through it, then what will happen? EMF will be induced. EMF will be induced, and this EMF will oppose, because it has property to oppose the change. How it will oppose? By inducing this EMF. Getting it? So this will oppose this change in flux by inducing EMF. Remembering that, so EMF will be induced, and EMF we can write is equal to minus of d phi by dt. Here this minus sign is exactly for that it will oppose. Okay, so this I can write minus L di by dt. So this is what EMF across the inductor coil, across the inductor. I hope you are understanding. Okay, next point here comes is that if let's suppose di by dt, means current is changing, definitely EMF will be this one. The point is, what will be its polarity? Okay, sorry. So the polarity, how we define polarity, that which end will be positive, which will be polarity of EMF induced, right? So see it here. So let's say this is our inductor, right? Some current I is flowing through it. Its inductance is L. Now there can be like two possibility for I. Either it may be increasing or it may be decreasing. Clear? So let me talk when if I is increasing. Clear? That implies di by dt is some positive, right? So it's increasing, that means it's positive. Now what will happen? The point is that here, like from this point we can't say exactly that when current is going basically this way, then magnetic field, whether north pole is here or north pole is here, because the coil, it can be like wrapped this way also, it can be wrapped this way also, but from this symbol we actually can't comment on it. So we need to define, or either we must be given, there is one dot convention also there, which exactly tells you in this case that if I am placing one dot here, that implying north pole is here actually of the magnetic flux that this current will be producing. Okay, so now if I am saying, let's say north pole is here, what it implies means the current is going this way, so that north pole is this way, this side, right side. Is it? And north pole of what? The magnetic field produced by this current. Even when this current is constant, still remember that still there will be magnetic field, still there will be magnetic flux. Getting it? Now what will happen? So when constant current is there, north pole is here, and there will be, like, you can write magnetic field through this coil. Now if I is changing, then that flux will be there, and that flux it want to keep it constant. Understanding? So when, like I'm saying, when I is constant, then this is the flux, and now this flux can have north pole this side, can have north pole this side also. So I am assuming, let's say north pole is this side conventionally, right? I have taken it dot, right? So in this situation, north pole is this side and current is what? Increasing. I am saying current is increasing. So if north pole is this side and current is increasing, then what will happen actually? Magnetic field will increase, mu naught into Ni, and that will result in more magnetic flux. But what coil will do? It will try to oppose that. How it will oppose? By inducing some EMF. So it will induce EMF that will create a flux in opposite direction. I hope you are getting the point here. I am saying north pole of this constant current will be rightward. If current is increasing, the flux will try to increase, but the coil will oppose that, and it will try to create a magnetic flux in opposite direction, means it will try to create north pole in this direction. And how? So for that, it will, like we can say, right? Understanding? So now in this situation, north pole will be this way. So it will try to, like, if I am saying this is the way current is going, actually this current, and north pole is outward, so it will try to basically induce current in opposite direction. Opposite direction means if current is increasing, then it will try to flow current in opposite direction, so that, like earlier it's going this way. I hope you are getting, like I'm saying, if it is going like this way, then that way it's like in front of you, towards you, it's north pole. So what will happen, the induced EMF will try to create or induce current in opposite sense. So in this sense, so it will be like trying to create current in opposite direction. So current is flowing this way, so if it is increasing, then it will try to induce EMF that will result in current in opposite direction, and that way it will oppose, is it? So if I is increasing, then the induced EMF will oppose the increasing flux, right? And this way, so I can write the induced EMF is mathematically given by minus of d phi by dt, and that is minus of L di by dt. And here you can see this is I, is this I, right? So if this is the positive, I am saying, let's say this is A and this is B, and then here I can write A will be at higher potential, so I can write VA minus VB, it will be what? L di by dt. It will be positive. But if VB minus VA, it will be minus L di by dt. In general term, I hope you understood this point. Plus minus, induced EMF, positive negative sign. I think like I tried to explain you, because this current is increasing, magnetic flux is this way, and it will try to increase, but coil want it to constant, means it want to oppose that increase. How it will oppose that? By inducing current in opposite direction, or you can say by inducing EMF, and that EMF is mathematically given by this way, and polarity we can decide. So if it is increasing, then polarity will be this way, so it will try to flow the current in opposite signs, or simple terms, because current is increasing, so it will try to decrease the current. How it will try to decrease the current? By inducing EMF in opposite signs. So I hope you understood this. So that is a condition. This is the symbol, how we can write it. Polarity, how we can decide. So polarity, it's not universal, it's like depends on the EMF, right? I'm like sorry, the current, whether it's increasing or decreasing. So second case, if I is decreasing, that means you can write di by dt itself will be negative quantity. Clear? So in this situation, see, again this is my inductor, right? Here current I is going and it's decreasing. So now what will happen? Again I am taking, it's going this way, it's creating magnetic field, magnetic flux in right direction. So it will try to, now current is decreasing, it will try to create more current. Understanding? So it will try to like this way. You can see positive. So it will try to flow current more in this direction. You can see the magnetic, now see current is going this way, right? This way. So it's like what? Towards you, north pole, is it? Now it will try to increase more current, so it will here positive, negative, so more current will be like going this way. So that way it will try to increase the current, means it will try to, because current is decreasing, so that means like we can say it will try to keep it constant. By how? By inducing EMF, and the polarity will be this way. So in this situation, see here it's A and it's B, is it? If we are going in a loop, is it, across this element, so if we are going in the direction of current, then what will we write? We write B minus A, is it? So VB minus VA, and that will be like, we can write, see, it will be positive because this is high, this is low, so I can write it's plus L di by dt in general terms. So one thing is, this is expression for this, okay? I hope you got it this point. Now I'm writing, because every time you don't have to like even think about this positive negative, we can even get some standard thing actually. And what is that? So in I'm going to write that standard relation is that if in a like a circuit, is it, moving in the direction of current means if this is a inductor circuit I, right? So this is, we are going A to B. In the direction of current means we are going from A to B. Circuit, like circuit analysis, KVL, KCL, you must be knowing that we will apply those things here also. So for that purpose, you don't have to like to worry every time like plus minus sign. I am telling you something simple thing for that. So if you are moving in the direction of current, then always take it. It will be VB minus VA. So VB minus VA is equal to minus of L di by dt. Always, whether it's increasing or decreasing. Now see how it will take care of everything. So if di by dt is increasing, understanding, then this quantity will be positive, and this quantity is positive means b will be like, b will be at like, this quantity is positive means b will be at lower potential. So lower potential minus higher potential should be negative. So if di by dt here it's positive, then you can see this quantity is coming out to be negative. So it's satisfying exactly this condition. It's satisfying this condition. Clear? Now next thing, if di by dt is negative, then what will happen? Negative, so it will be like, if you substitute the value, then it will come some minus of something. Understanding? So minus will cancel out, and then you can see this quantity, this will be positive, b will be positive. So you can say b minus va, and this overall quantity will be positive. So it's automatically taking care of everything, increasing and decreasing current when you are applying or going in a loop in a circuit. Understanding? So that is, we write symbol this way, and here like if current is constant, flux will be there, but there will be no induced EMF across the coil. If current is changing, then flux will change. Coil has property to oppose that change, and that opposition will be by creating an induced EMF. The induced EMF polarity will be such a way that it opposes the change in flux through the coil, is it? And we understood that how. So depending on if I is decreasing, then it will like current, it will try to increase current in the direction, same direction. So here it will be positive, negative, and this we can understand it will be positive. So if current is increasing, in that case this will be the situation. You can see like A will be a higher potential. So if I am writing VB minus VA, this is normal terms, general terms, minus d phi by dt. VB minus VA, then it will be minus. If I am writing A minus B, then it will be positive, is it? But in general terms, you don't have to worry about A minus B, B minus A. You can always write in the direction of current. Remember that in a circuit moving in the direction of current, then we can always write, is it? We can always write this above relation, is it? This one. So I hope you understand. Let me show you this with example. Okay, just one more point. So in general term, if this is some coil, then this is equivalent to actually this inductor, right? This coil, any coil is equal to inductor of inductance L. Clear? And if an inductor is also having resistance, if the coil also has some resistance, right, then we write this inductor coil. So we L and its resistance R. We better write it current I, is it? This is A and B. So this we equivalently you can write basically inductor and resistance in series, is it? So R L, this is current I. Okay, so that is like if it is having some like resistance also. Let me just show you one thing actually. So consider this is a part, consider a part of complete circuit, okay, and that part is this inductor, some battery, resistor, let's say A this is B, let's say it's 5 ohm, 5 volt battery, 2 Henry inductance and current I. And now I am writing, you are asked to find VA minus VB in the following cases. So what are the cases I am giving you? Case A, if I is equal to 2 ampere and constant. Clear? Alright. Now let me show you how we will write. So we write it from like by KVL, we consider some potential VA. Remember this simple thing, it's not much complex, don't get confused. This battery and resistor. Current I 2 ampere, 2 Henry, 5 volt, 5 ohm. This is B, this is A. Okay, so normally how we go? We start with VA. We don't know what is the potential because we are not even asked to find the potential of point A in absolute terms. We just need a difference. We will simply go with the KVL just like that way. So VA, whatever it is. Now I'm saying through this. So minus L di by dt. Remember that. I do not care whether current increasing, decreasing, what is happening. Always minus L di by dt. Here I know already if I am going from here, like from this point to that, then it will add. So plus 5 volt. Now across the resistor, I am going in the direction of current. So across the resistor, current flow from high potential to low potential. So that means this should be high and this should be low. So if I am going in this way, then it will be minus. So it's minus I, that is 2 into R is 5 equal to VB. And here you know this di by dt is constant. So that means it is simply 0. Clear? So I can write VA minus 0 plus 5 minus 10 equal to VB, and VA minus VB is coming out to be, this is plus 5 minus 10, it's 5 volt. This is answer. I hope you understood. So here you can say A is still a high potential, right? I solved it actually. All right, let's say B part. So if DI means I is again 2 ampere and di by dt is also 2 ampere per second. Clear? Now in this situation again I will go exactly this way. So for that also, this is my inductor, battery, resistor, B, this is A, current I 2 ampere and 2 Henry, 5 volt, 5 ohm. Clear? So now again same manner exactly. I hope you are finding it easy. It's not much difficult. So in circuit also we can deal with inductor. Up to now we have like done problems with the inductor and capacitor also. Later on we will see things with the capacitor too also. Like so let's see here. So again I will write VA. Now minus L 2 into di by dt plus 5 minus 2 into 5 equal to VB. Clear? Now di by dt is what? It's increasing, so it's positive plus 2. So then I can substitute it here. So this is VA minus 4, 2 into 2 4 plus 5 minus 10 equal to VB, and what it is coming out to be. So it's basically minus 14 plus 9, so it's minus 9, and we are getting here VA minus VB is equal to 9 volt. Clear? In exactly same manner, if C part I is equal to 2 ampere and di by dt it's decreasing and let's say minus 2 ampere per second, then what will happen exactly? Now current will decrease, so it will what? Positive. It will be this way. Understanding? You can see it will try to increase it. So now I can write, see here, VA again. This is A, inductor coil, battery, resistor, and this is B, this is A, and ampere like I, it's 2 ampere, 2 Henry, 5 volt, 5 ohm. So I can write VA minus 2 into di by dt plus 5 minus 2 into 5 equal to VB. Clear? And again, so this is VA. Now my di by dt is minus 2, it will be plus 4 plus 5 minus 10 equal to VB, and this comes out to VBA minus VB is equal to only 1 volt. So this manner, like we can deal with the problem having inductor also. I hope you understood when we need to take potential difference across the inductor, positive, negative, in which direction, that should be clear, and what is exactly inductor, and it's measured in Henry. Let's see more cases on it. Okay, see next problem. So here in the we are given again a part of circuit. So in the circuit given below, we are asked to find the potential VC. This is the point C. So here potential is asked, and data given I1 di1 by dt across this resistor is 2.5 increasing, 10 ohm resistor, 4 Henry like inductor, and 2 Henry inductor another here, one battery is connected. Potential of point A here is given 10 volt and B is given 40 volt. So this is the information given to us. So let's see. So now we will try to solve it. So we will try to deal it part by part, whatever the information we can have. So first thing, like we can go from here. So I can write V, if I go in the direction VA minus I1 into R, that is 10, is equal to VD, and VA is equal to what? 10 minus this is I1 1 into 10 equal to VD. This implies VD is coming out to be 0 volt. Okay, we got one. So VD is 0. Now next, let me get up to here. So here I can write, here I am going in the direction of current, so I can write VB minus VD. This is for inductor across dB, you can write, or across inductor 4 ohm or 4 Henry inductor, right? So here I am going in the direction of current, so I can write VB minus VD is equal to minus L, that is 4 into di2 by dt. Clear? VB it's given 40, D it's we got 0 equal to minus 4 into di2 by dt, and this implies 440. This di2 by dt is coming out to be minus of 10 ampere per second. So we got this, we got that, and similarly now I can go in this direction. So first thing is here, because I3 and di3 by dt is also not given. I3 I can get easily, but I don't even require that. So I can write I1 equal to I2 plus I3 by KCL at point or at junction D. So this is the current coming, going, and this way. Now differentiating this, di1 by dt equal to di2 by dt plus di3 by dt. This is how much? 2.5. This is how much? Minus 10 plus di3 by dt. This implies di3 by dt equal to 12.5 ampere per second. This is also increasing. Clear? Alright, now we can go from D to C. So I can write VD, this is plus 10, and now I'm going in the direction of current, so I will write it minus L, that is 2 into di3 by dt equal to VC, sorry. Clear? So first thing is VD is 0 plus 10 minus 2, and di3 by dt is how much? It's plus, and that is 12.5. So it's plus 12.5 equal to VC. So this implies I am getting 0 plus 10 minus, here it will be like how much? 25 equal to VC, and this implies VC is equal to minus 15 volt. So this is the answer. I hope you understood this problem also. Let's see another case. Okay, so next let's see how an inductor behave when it is connected across an battery. So we will write that current, consider an inductor connected across a battery. So we have here one inductor and one switch, and this is another battery. So it's connected across a battery of EMF E, inductor L. Initially we can write switch was open and current across through inductor is 0. So this is the information given to us. Just wait. Okay, so now this situation I can write basically I is equal to 0 at t equal to 0 because it's given, right? And let switch is closed at t equal to 0. So if switch is closed at t equal to 0, then I can go in the circuit with KVL, apply KVL in circuit. So starting from here I can go plus E, so it's E, then current assuming flowing this way, so then I am going in the direction of current, so I can write minus L di by dt equal to 0. This implies here this is L di by dt is equal to E, and di equal to E by L into dt, integrating both sides 0 to t, 0 current 0 and t, let's say it's I, so we are getting I is equal to Et by L minus 0 and I is equal to E by L into t. So we can see this is how actually the current across an inductor is varying. If I plot its curve basically, so then here this is I versus t, you can see this is a straight line graph passing through origin, so the graph will be like this starting from origin, right? So this is the variation of current across the inductor as function of time. So if only inductor or ideal inductor is connected across the battery, the current grow linearly in the inductor. Now see here actually that I will calculate. In this situation current is growing, is it? That means battery is supplying some energy, is it? So that means inductor store energy. I will calculate that. Okay, so this is the ideal inductor. Let's see if inductor and resistor is connected across a battery, then how our current vary. So that we write growth of current in an inductor. Okay, so next consider, let's say if across an inductor one resistor is also connected and both connected to a battery. So we call this is L inductor or resistor, so we call this is LR circuit actually. Okay, so let's see the growth of current in the LR circuit. So again here also t equal to 0, I is equal to 0. Initially the switch was open. Now t is equal to 0, switch is closed. Right? Battery, EMF like E, resistor and so on. So now what will happen? T is equal to 0, switch is closed, some current I will start increasing, start flowing. Another thing, just for your information, try to understand it. What is happening? Initially current in the inductor is 0. Getting it? What is the property, behavior of inductor? It does not want to change it. So what inductor will try? Inductor initially will try to maintain the current 0. Understanding? So that means then current, because battery will push it against that, so battery will try to increase the current, it will try to decrease it. So overall we can say the current will start from 0 and it can't increase immediately. Getting it? It will start increasing slowly and we will get the expression mathematically also. That was logically we can understand, because inductor will try to oppose whenever there is some increase in current in the inductor, it will oppose that. So it can't increase fast, it will increase slowly. Understanding? Let's write it, let's see it here. So what we can do, right here, apply KVL in the loop, right? I'm assuming current is I and it's changing at the rate of di by dt. So going from here, then I'm going across this, so it's plus E across the inductor in the direction of current, so it's minus L di by dt. and in the direction of current, so it's minus I into R equal to 0. I hope everyone is clear with this relation. I started from here going this way, so plus, so this is plus E. Inductor in the direction of current, I don't know what is happening, but I will directly write minus L di by dt. Across the resistor, again I am going in the direction of current, so it's always minus IR. Up to here, let's rearrange it. So this implies I can write E minus IR equal to L di by dt, and this implies L di by E minus IR equal to what? Dt. Clear? And next I can integrate it 0 t. What is the current in the circuit? 0. It's clearly starting from 0. So I can write 0 to some current I. Clear? Let's integrate it. So integration on this left part will be, this is L, and integration of this is ln E minus IR divided by minus of R limit 0 to I, and on this side it's simply T, and substituting the limit also, so I'm getting simply T. Multiply it, and so it's substituting, this is ln E minus IR divided by E, and this side it's minus RT by L. Clear? And here I have done directly. If I am substituting the limit 0, then it will be ln E. Substituting the limit I, then it's E minus IR. So it's ln E minus IR minus ln E, and that can be written as this way. So this implies I'm just removing ln, then it's coming out to be E minus IR divided by E equal to E raised to power minus RT by L. Clear? And this implies just rearranging it, multiplying, taking it. So I is coming out to be E by R. It's 1 minus E raised to power RT by L. This is the way current will be increasing in this circuit. If I plot this graph, so you can see here at this is I versus time, is it? T equal to 0, if I substitute e power 0, that is 1, and it's coming out to be 0. So current will start from 0. T is equal to infinity, right? I can substitute here T equal to infinity. What is happening? At infinity, this will be e power minus infinity, 1 upon e power infinity, that will become 0. Current is becoming E by R. So at infinite time, and it will be increasing this way. So the current at infinite time will finally become E by R. So this is the variation of current in the inductor. Now I can tell something more. First thing is this L by R, we define it tau. This is also called time constant. Is it? This is time constant. So L dimensionally, you can also check it, L by R coming out to be time in like dimension, and we write it tau, and that is termed as time constant of the circuit. Okay, one time constant T equal to tau, this is called one time constant. It is the duration in which current grow from 0 to 63.2% of maximum current, right? That is one time constant. Another thing here, you can see T is equal to 0, I is equal to 0. What it means if I look at it logically, that means at T is equal to 0, as soon as I am switching it on, inductor is completely blocking it. It's not allowing any current. Getting it? So that means T equal to 0, current through the circuit is 0. This implies at T is equal to 0, the circuit is behaving like open circuit, or you can write instead of circuit here, it's basically inductor. So t is equal to 0, inductor is behaving like open circuit, so the circuit will be like this. This is inductor, that is open circuit, resistor, battery, switch is closed, and this is, so t is equal to 0, the circuit, this circuit is equivalent to that circuit, right? Now I can erase this part. So similarly, next point is at t equal to infinity, means after long time, we call it steady state also. So sometime you will be asked in the problem, find the current through the circuit at t is equal to 0, means initial and in steady state. So that means it is talking about infinite time. Clear? So in this situation at t equal to infinite steady state, I can write here, see, e power minus infinity means 1 upon e power infinity, that will be 1 upon infinity 0. So it's coming out to be e by r. So I is equal to, you can write I max, and that is equal to e by r. Independent, I is independent of inductor. It's not depending on inductor, and you can see it's the maximum current, right? And that is equal to simply e by r. So this implies what is happening, it's just like at infinite time, it's behaving like there is nothing, there is no inductor is present in this circuit. Getting it? So the circuit, or I will write better here, inductor behave like a wire or conductor with zero resistor. Clear? So this implies the circuit will be what? This switch open closed at t is equal to, this is at t equal to infinity, e r. What will be the current in the circuit? You can say e by r. Simple thing. Getting it? All right. So that is how, so you should remember these are important points. So here we got this t, and that is how your inductor is behaving at 0 time and okay. So here up to here, next point here, this is also important. If there is any change in the circuit, change, what it mean? Maybe inductor is changed, maybe battery is changed, maybe resistor is changed. Remember that, is it? So if there is any change in the circuit, then the instantaneous change in flux through inductor will be 0, or I will write better in another way, there will be no change in flux through inductor. Immediately if you are changing something, some power property, some parameter in the circuit across the inductor, the flux will remain constant, is it? So just like here, so at some time t, let's say inductor is L, is it? This explanation I will say, let's say let at time t, is it? Time t, current across the inductor, let's say I1, inductance L1. Okay, now L1 is changed to L2. So what will happen? What do I mean, like whether I will say the current will change or not, is it? So the point is that flux will not change, current can change. I am not saying that current will not change, flux will not change. So this implies initial flux phi I should be equal to phi final, and that means phi I is equal to L1 I1 will be equal to L2 I2. So if L2 is changed, then I will change such a way that flux will remain always, not always, immediately constant. Getting it? So this is about growth and time constant inductor, how it behave when it's connected across a battery with the resistor. So this is the growth of current in LR circuit. I hope you understood this part. Let's see next case. Okay, see next simple problem. So at t is equal to 0, switch is closed here. So this is a switch which is closed at t is equal to 0. Then in the circuit shown after long time means like initially if I say this is the current, so what is the current? I1 is equal to E by R after long time. Inductance of inductor is made eta times lesser, that means L by eta than its initial value. Find out the instant current just after the operation. Which operation means when the inductance is made eta times less, is it? So I can write L is changed to L by eta. Clear? Right now the thing is flux through inductor will remain constant. Clear? So initial current is this, so I can write L into I1 initial should be equal to L by eta into I2, right? So this implies I2 is equal to what? LL gets cancelled, this is eta times of I1 and I1 is E by R, that is eta times E by R. That is simple problem. So this way we can see when inductance is changed, immediately current will change in a manner such that flux through the inductor remains constant. Okay, so this is about growth and some property of basically inductor, how it behave. Let's see similarly, if let's say initially inductor is let's say flowing current through the inductor is maximum, now it's connected across some resistor, then at that time it behave like a power source, energy is stored in the inductor. We will calculate that, and in this situation the current through the inductor will decrease, and let's see its variation how it happened. Okay, see, so here we have one inductor resistor connected across this way and switch like this, and this complete system connected across a battery. Okay, so t is equal to 0, the switch is closed. Resistor R and inductor L, EMF E. At time t, some let's say let current across inductor is a current through inductor is I. So let's say I is the current flowing across the inductor, right? Now what I am doing at this moment of time, at this moment, if inductor is disconnected, what will happen? The current through the inductor will not become 0 immediately, because current will be there, some flux will be there, so flux will store. Basically I can say the energy across the inductor will be stored, or in the inductor some energy will be stored, and that will not become 0, is it? So here current is there, is it? Now it may be reconnected across in other circuit, right? So this inductor, which is basically an inductor, this is inductor which is having some energy stored in it, we write this is called active inductor. Active inductor means a inductor, active inductor, an inductor which is already having some energy stored in it is called active inductor. inductor means which has energy already stored. The current is not zero, means the current is non-zero when it is connected in another circuit. When it is connected in other circuit. So initially at that time this current will not be zero. Then this is called active inductor. Okay, so let's see next, decay of current in inductor connected across the resistor. So sort of like you can say here an active inductor is connected across some resistor, right? Let me just draw its diagram. So there can be two cases, two possibilities, both mean same. Another way, one way is simply I am having an active inductor, means which is already having some energy stored. So initially the current is I naught and it's connected across some resistors. Now here energy is supplied by the inductor, so it's like decay. Here current will start decreasing. So one way is this way. Another case is, let's say here I am having one battery connected across inductor and resistor. So now what I am doing is initially I am switching it like switch 1 is kept on. Is it? Now what will happen? Across this inductor current will grow. Is it? So let's say after long time I disconnected it and connected switch is connected to 2. So after long time switch is shifted from position 1 to 2, right? So in this situation also this circuit will be just like this. So now here current will start decreasing. Let's get the expression for that. So that is also easy, it's not complex. Again we will do what? We will apply KVL in the circuit, we will write the relation, we will integrate, and that's all. We will get the answer, we will get the expression. So here also I can go exactly same way, apply KVL L in circuit. So I am here assuming let at t equal to 0, I is equal to I naught. Some I current, not current is there already in the inductor. Going this way, so switch is closed at t is equal to 0. Now remember here I am making this, when switch is closed I am making that time as t is equal to 0. Here initially it was like kept closed for a long time, then it's opened and shifted to this point 2. Now that time I am resetting to again 0. Remember that. So both mean same. So this circuit will be just this and it will be like separate out. So in this situation I can go this way. So here it's what? Minus L di by dt. Across the inductor here I am going in the direction of current. So again it will be what? Minus IR equal to 0. Clear? What it implies, I can this right. That means minus L di by dt equal to I into R. And this implies di upon I equal to R by L minus into dt. Integrating 0 to t, it's I naught to I. Clear? Because here you can see initial current is I naught, it's ln I. I will write this I to I naught minus RT by L. This implies I is equal to I naught e raised to power minus RT by L. So here you can see the graph for this I versus t. T is equal to 0, e power 0, that is means 1, I is equal to I naught. Starting from I naught and t is equal to 0. T is equal to infinity. What is there? E power minus infinity. 1 upon e power infinity 0. So 1 upon infinity, that means complete 0. So final current is becoming 0. So it's decreasing and finally becoming 0. So that is the way. So here we can call it decay because the current is decreasing here. So this is our current. So again here we write L by R equal to tau. This is called time constant. Clear? So in this case, like your current will be decreasing. So one time constant I can write. One time constant is means it's initial current I naught. So one time constant it's T equal to tau. That current become 36.8%, or I will write 0.368 I naught. Is it? So one time constant is the duration in which I decreases to 36.8% of initial value. So this is all about decay of current, right? Okay, let's see some problems based on the concept that we recently studied just like back. So here in the following circuit, switch is closed at t is equal to 0. Find the current I1, I2 and I3 and t is equal to 0 and t is equal to infinity. Initially all currents are 0. Okay, so initially all currents are 0. That is also mentioned. So now like at t equal to 0. First thing is I told that switch is closed at t is equal to 0. How inductor in the circuit we have at t is equal to 0. So inductor at t is equal to 0, inductor act like open circuit. I just told you. So that means the circuit at t is equal to 0 when switch is closed will be this. This is open circuit and this resistance. It's R, R, R and E. Current I1, I2, I3. So what I can write directly, I3 will be 0, t is equal to 0 and t is equal to 0, I3. Open circuit, no current. From here we can say normal current will be flowing in this way. So this implies I1 equal to I2 and that can be written as E by U. So this is the circuit at t is equal to 0. Clear? Similarly at t equal to infinity. So infinity, how an inductor behave? Just like wire. Inductor we have like a conducting wire at t equal to infinity. So means the circuit will be like this. Circuit at t equal to infinity will be like this. Clear? R, 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 E. This is I1, I2, I3. Clear? So now this is what? Resistor in parallel, R by 2 plus R. So R equivalent is equal to what? 3R by 2. This implies I can write I1 is equal to E by 3R by 2, that is 2E by 3R. This is what? I1. Now this I1 current will what happen? Divide equally because these two resistors are what? Equal. You can see R and R both are equal. So we can write this current divide equally among I2 and I3, and this implies I2 equal to I3 equal to I1 by 2, that is E by 3R. So this is the current. So I hope by this like you got the application that how an inductor behave at t is equal to 0 and at t is equal to infinity in a circuit. We are going to see more applications.